All right, I'd like to derive a series of formulas that we use with universal gravitation. And I'll probably do this in a series of short video clips and merge it all together and make an ed puzzle, things like that. So this is primarily for cohort A, since you only come to school one day a week, thanks weather, among other things. But if you're in cohort B and you're absent, this would be great for that also, or just as a review. I need a haircut. Anyway, the first thing we're going to do is derive escape velocity. That actually I had mentioned it was in section 13.2. That's incorrect. It's example 13.2 from chapter 13. And we're going to do this based on universal gravitation. So the first thing I'm going to say is we are going to think about the fact that this is an energy problem. So think energy. Well, what is an escape velocity? An escape velocity is the speed you would need to launch something directly off the surface of a planet, such as the Earth, without any additional speed, fuel, force provided. So it's not like how we launch rockets, where we have a continual thrust for several minutes as they go up into orbit. It is an initial launch, like you would have a really strong cannon go kaboom, and it gains that escape velocity initially, and then it slows down as it reaches orbit. So in terms of thinking energy, essentially as soon as this object is launched, we're going to think about the energy it has then, and then we're going to think about the energy that we're going to have in orbit, or the minimum needed not to go into orbit, but to escape the Earth's gravitational field. So this is not orbital velocity, this is escape velocity. So if we want to have a spacecraft go away from the Earth to, say, explore the outer parts of the solar system, like the Voyagers did, New Horizons, things like that, we got to get out of the Earth's gravitational field. So thinking about energy, we're going to think about E initial equals E final. And this initial is going to be just after this is shot off the surface of the Earth or a planet, and this is going to be once you escape the Earth's gravitational field, which technically would be an infinite distance away, but obviously it approaches infinity asymptotically, so when you get pretty far away, I guess. In this case, we want to think about our initial energies, KEI, initial, plus UGI, equals KEF plus UGF. So initial kinetic energy, initial potential gravitational energy equals final kinetic energy and final gravitational potential energy. Well, we've already talked in cohort A about the fact that gravitational potential energy is zero at infinity once you get to an infinite distance away. And to find the minimum escape velocity is normally what we're looking at. Basically, we need enough where we would be slowing down as we leave the Earth's gravitational field and just getting to zero speed as we got to an infinite distance away. So essentially what that means is this is going to be 0, and this is going to be 0. Looks like someone looking at you. At any rate, so we've got 0 total mechanical energy at infinity. What do I have launching from the Earth? I'm going to have something shot up, so that's going to be kinetic energy. So that's going to be 1/2 m, and this is going to be mass of the object times v escape squared. Okay, what about this gravitational potential energy? Well, we can't use mgh because mgh is only when we have a constant value of g, and that's a near-Earth approximation. So what we've got to do, I'm going to have to move this over a little bit, is we've got to use our formula for gravitational potential energy. Again, for cohort A, we derived that in class on Monday. So that is negative big G, which is the universal gravitation constant of 6.67 times 10 to the negative 11th, m1, which in this case is going to be mass of the object, times mass 2, which in this case might be, say, mass of the Earth, could be any other planet, over r. So since I'm adding a negative, I can think of that as subtracting. So what that means is I'm going to move this to the other side of the equation. M object v esc squared minus g m object times m earth over r equals 0. So now I can go and I can say 1/2 m object v escape squared equals g m object m earth over r. Why did this become positive? Because it was negative on the left-hand side of the equation. I added it to both sides. So one of the favorite things I get to do in much of physics is to cancel things out so that m object is on both sides. I'm going to get rid of that. I'm going to divide both sides by 1/2, which is basically multiplying both sides by 2. So I end up getting v escape squared is equal to big G, mass of the planet, or in this case mass of the Earth. Should put times 2, because I basically multiplied by 2 over r. To simplify that and just get escape velocity, v escape equals radical 2 big G mass of the planet, in this case if we're talking about the Earth, over r. And that's it. So mass of the Earth and the radius of the Earth are things that we might want to know, but oftentimes the AP likes to use things in terms of variables as well. In the case of the Earth, again, I know that the mass is 5.98 times 10 to the 24th kilograms. Forget the radius, it's around something times 10 to the 6 meters, but I'll look that up shortly. Thanks, that's video part 1. Okay, in this part of the universal gravitation lecture, we're going to talk about how to derive orbital velocity. So the last time we were deriving escape velocity, and also derive Kepler's third law of planetary motion. And the only reason I'm going to do that, it's not on your formula sheet, but occasionally I've seen things come up where basically they're asking you to do that derivation or understand that derivation on an AP exam. So I'm going to do it here. Hopefully it's something that'll be helpful to you. So in this particular case, when we're thinking about this, you really want to think forces, at least initially, when we're doing this. So for escape velocity, we wanted to think about conservation of energy, and in this case, we're thinking about forces. Well, what the heck is an orbital velocity? It is the speed at which an object can maintain a stable circular orbit around a spherical body like a planet or star or something else like a black hole that would have a strong gravitational field. So if you're going too fast, basically what would happen is an object that's going around a planet would then end up flying away. So if this is the Earth and we're going too fast, we're orbiting over here, we're going to fly out of the Earth's gravitational field. If we end up going too slow, we're going to sink into the Earth or be gravitationally crash into the Earth. So we need a very particular orbital speed, and that's true of any object orbiting another object. When we think of orbital speeds, we tend to think of one object, such as the central body, having much, much more mass than the object that's orbiting it. So for example, the Sun has much, much more mass than the Earth. The Earth has much, much more mass than the Moon. How much more? Well, I'm not sure about the Sun and the Earth. Oh yeah, I am. I think that's around 1 to 10 million times as much mass. of the sun as the Earth, but the Earth has about 100 times as much mass as the moon. So we're not talking about like a binary star system where they orbit a common center of mass, which I think is called a barycenter, or something like that. Okay, so how to go about this, thinking about forces? Well, obviously this is a chapter with universal gravitation, so I've got to be thinking about the fact that universal gravitation is going to be keeping an object in orbit. Okay, well, if something's in a circular orbit, what kind of force is that? In general, we think of that as a centripetal force. So I could start with the definition of centripetal acceleration. I'm going to start with this. It should be an A. Okay. Any sort of centripetal acceleration, and that is on your formula sheet, is v squared over r. Well, what is that v? In this case, it's going to be v orbit. Well, if I know an acceleration and I want to find out a force, all I do is multiply that acceleration by mass. So while this, which is centripetal acceleration, is on your formula sheet, the formula for centripetal force is not, hey, you should be able to figure this out, and I'm going to call it m satellite. This is going to be the mass of the satellite around here. So that's going to cause the centripetal force on the satellite. What's causing that? Because this is really just another word for net force. It's the gravitational force between the planet and the satellite. So we're going to use our general gravitation formula. That's big G times mass 1, and in this case that's going to be mass of the satellite, times mass 2. In this case that's going to be mass of the planet. And I could think of Earth as the planet, but again it could be any other large object. And that's going to be over that distance squared. So if Garrett Cox is looking at this, he's going to be excited because he likes when mass cancels out. And in fact, at least one of these masses cancels out on each side. That's the mass of the satellite. The other thing is one of these r's cancel out as well. So I'm pretty close to getting this derivation already. I'm going to get that v orbit squared is equal to big G m Earth or m planet over r. So to solve for that, v orbit, take the square root of both sides, radical G m Earth over r. Okay, that's pretty straightforward. Now if we compare this to what I did earlier with escape velocity, you remember v escape was equal to radical 2 G m Earth over r. So hopefully it kind of makes sense that something's going to need a higher speed to completely escape the Earth's gravitational field as opposed to orbiting in a gravitational field. So that's just a little bit of an aside. Well, what about this Kepler's third law of planetary motion? Well, here's kind of how we think about that. I'm going to see if I can switch to a different color for dramatic effect. I might use red. We also know, although we've got this, we can also think about velocity in a more general way. So I could think of this as that just velocity is equal to displacement over a time interval. And I'll leave the deltas out. It should be dx dt, I guess, since we're in calculus-based physics. Well, what is that around a circular object? So the orbit would be the circumference, which is 2 pi r over that time interval. That's t. So that's another way of thinking about that. Okay, so what I can do is I can set these two equal to each other. that down, switching colors again for dramatic effect, I can say radical G, mass of the planet or the Earth, over R is equal to 2 pi R over T. Well, that's kind of messy, but that's okay. I want to get rid of a square root thing, so I'm going to square everything. So everything on the left is going to come out of that square root sign. So that's going to be G, mass of the Earth, over R. Square everything on the right side. So that's going to be 4 pi squared R squared over T squared. I'm going to rearrange that and move that around to solve for T. So what I'm going to get is T squared is equal to 4 pi squared R squared, but I'm going to multiply that on this side as well. So 4 pi squared R cubed over big G times the mass of the Earth or planet. And that's it. You might say, so what? Well, it's a fairly complex mathematical relationship, and it basically says the period of rotation, the time period to go around an orbit for a planet or any sort of celestial body, that time squared is related directly to the cube of the radius. And that is a very classic thing to understand. So that's that. All right, in this part of the video, we're going to look at trying to understand and derive the total mechanical energy for an object in a circular orbit around, again, a planet, star, other large body. So something to remember from the derivation for orbital speed is we found that V orbital was equal to the square root of big G, which is 6.67 times 10 to the negative 11th, times the mass of the planet. In this case, we'll call it Earth. And that's over R. So that is true for something in any stable orbit. Okay? Well, how do we find the total mechanical energy for an object in a circular orbit? That's fantastic. We're going to look at both gravitational potential energy and kinetic energy. So, kinetic energy plus UG. And we're going to call this, we're going to look at it for a satellite. Could be a planet or a moon or something like that. So we start off with our general 1/2 m. This is going to be m satellite, v orbit squared. Okay, and u grav is going to be negative. So I'm going to subtract that. Big G, m satellite, m planet. In this case, it's going to be the Earth. Over R. So that's something, negative G m1 times m2 over R, something you should be starting to get pretty comfortable with. Okay, well now what do we do? Well, I want to substitute this in for that. 1/2 m satellite. If I square this, that just takes away the square root symbol, times big G, m Earth, over R. put this in a little more friendly form. Nope, that's not what I want to do. Big G in front, M satellite, M Earth. Since this is basically multiplied by half, that's going to be over 2R minus big G, M satellite, M Earth over just R. So basically this is 1/2 minus 1. So our final total mechanical energy for an object in a stable circular orbit is equal to negative G, mass of the satellite, mass of the planet, in this case it's the Earth, over 2R. Why over 2R? I had plus 1/2 subtracting a whole. I don't know why I used a capital R here. Or down there. I don't know. I'm just mixing things up. At any rate, so it's a negative total energy. That's always going to be true for an object in a stable path. So an object that's orbiting in a stable path will always have a negative total mechanical energy. You're only going to end up with this special case of negative 1/2 of the gravitational potential energy if we have something in a circular orbit. If we have something in an orbit that's elliptical, so let's say that's the Earth, is here, and we've got an object in an elliptical path, so something like this. Ugh. What we would end up finding is pretty close here. We have a greater percentage of kinetic energy and a smaller percentage of kinetic energy out here. So more gravitational potential, less kinetic, more kinetic, less gravitational potential. The total for this object and the ellipse amount of energy would still be the same, but the ratio between those would vary as you're going through this path. For a circular object, always going to be that. All right, I'm going to be doing 2 examples of sample problems that go along with Chapter 13, which is universal gravitation. The first example is I'm interested in finding the orbital time for the International Space Station. That's the ISS. Things that I'm going to need to know, and I should look up to see if these are in your formula sheet or not. Maybe, maybe not. I doubt it. I do know it's somewhere in your textbook. Don't think so. Mass of the Earth is 5.98 times 10 to the 24th kilograms, so that's a lot. And the radius of the Earth is 6.37 times 10 to the 6 meters. So that's 6,370 kilometers. That's somewhere around about 3,800 miles, something like that, 3,700 miles, I think. So the Earth is around 7,500-ish miles in diameter. I don't know the mass of the space station, so I'm going to put that as a question mark. If I have to use a variable, I'll put it as m. My hope and my bet is, if I need to, it'll cancel out. So what I need to think about, and one thing I do need to know, is the height at which the International Space Station orbits above the surface of the Earth. Because when we're calculating things, our r is our distance, isn't going to be the radius of the Earth, it's the radius of the Earth plus the height of that International Space Station. So I did just look that up, and it's about 250 miles. So the orbital altitude, kind of weird to call it altitude, so now I'm going to have to convert that. So 250 miles times 1.6, I believe it's 1.61 kilometers, or 1 mile, times 1,000 meters, 1 kilometer. I guess I could have just done 1,610 meters per mile. It's going to give me something where I'm ending up with 402,500 meters. So I think that's 4.02 times 10 to the 5th meters. All right, so I could do this just with Kepler's third law, which I derived. And if I don't remember that, I might have to derive it again. So I did derive it earlier in the video. So to refresh your memory, I end up getting that t squared is proportional to the radius cubed. So I'm going to have 4 pi squared r cubed, and all that's going to be over g, big G, times mass of the Earth. So there's a reason why Kepler's third law is kind of nice to know. And again, I could derive that from my understanding of orbital velocity and then just the general velocity of something going in a circle as being 2 pi r over t. So I'm going to keep this t squared over here. 4 pi squared. So I'm going to put these together. 6.37 times 10 to the 6th plus 4.02 times 10 to the 5th squared. Parentheses are going to be kind of important here. Over g, which is 6.67 times 10 to the negative 11th. And the mass of the Earth, 5.98 times 10 to the 24th. So I get that t squared is equal to 3.07 times 10 to the 7th seconds squared. So I get that t is equal to 5.54 times 10 to the 3rd seconds. So that's 5,540 seconds. Let's put that into times a little bit more that we know. So there's 60 seconds in a minute. So when I take that and divide it by 60, which of course, did I remember my calculator? Nope. Here it is. It's around 92 minutes. 92.3 minutes. If I want to do that again, to get hours, .54 hours. So that's a short amount of time, right? So it's going very fast as it's close to the Earth. As you get further and further away, we're going to see that the orbital speed actually decreases. All right, this is example 2. It's the final example I'll be doing for chapter 13. Probably should have put that. A bunch of this stuff, oh well. And that's going to be finding the altitude and speed of a satellite in geosynchronous orbit. Well, what the heck is a geosynchronous orbit? What it means is that it rotates at the same speed as the Earth and stays over the same spot on the Earth. So it's a very special orbit we use for things like weather satellites and things like that. The interesting thing is geosynchronous satellites can only stay in orbit above the Earth's equator. Because if you're anywhere else, if you're orbiting, you're going to basically not move, or you're not going to stay over the same spot. So if you ever see videos of things that are taking pictures of the Earth and it says it's a satellite or a stationary satellite, it just means it happens to be a geosynchronous or a satellite. So we're going to look and find what that altitude is in meters or maybe kilometers, and the speed in terms of meters per second. All right, so these are things that we had written down before. Radius of the Earth, mass of the Earth. This was mass of the space station. I'm going to call that mass of the satellite. And I don't know what that is, but hopefully if I need to know that, I'll just use M for right now. Okay, so things to think about. first off, I know that v is equal to dx dt in general. And for an object in circular motion, we're going to say that's 2 pi r over t. Okay, well, we don't know what this r is yet. We should know what t is, because if it's a geosynchronous satellite, it's going to orbit at the same rate of the Earth. So what that means is, with this t, it's going to be 1 day, 24 hours. But I want to find that in standard units, which is seconds. So there are 60 minutes in an hour and 60 seconds in a minute. So there's 3,600 seconds over 1 hour. So the time we're looking at here is 86,400 seconds. Okay. So when we think about that, we're going to go back and kind of do our Kepler's third law thing, and we're going to relate basically this orbital velocity to the orbital velocity we figured out before. So I'm going to say that we had figured out before was the orbital object using centripetal force and gravitational force. We figured out was radical G, m Earth, and all that over r, just the radius of the Earth. Okay, and over here we're going to say that's 2 pi r over t. So I'm going to say G, so actually I'm going to put numbers in at this point, except for R. 6.67 times 10 to the negative 11th. Mass of the Earth, 5.98 times 10 to the 24th. Extend that square rootage thing, and all that over R as well. So it helps me when I square everything on both sides. So I end up getting 4 pi r squared. When I square this, it gets me 7.46 times 10 to the 9th. And that equals this, which is 6.67 times 10 to the negative 11th. It's the mass of the Earth. All over R. So now I'm going to do some cross multiplying and re-algebraing, and I basically do get 4 pi r cubed equals all these numbers put together. So and so I can now do some maths, and I can get that r cubed is going to equal 7.54 times 10 to the 22nd. Take the cube root of that. I get that r is going to equal 4.225. And it should be 10 to the, I believe 10 to the 7th. And you might think we're done, but we're not done, because that is the distance that is away from the center of the Earth, This was asking about the altitude. So, to find the altitude, switching colors for dramatic effect, so that's 4.225 times 10 to the 7th minus the radius of the Earth, 6.37, all in meters. So I guess I could have subtracted 0.637 times 10 to the 7th. So the altitude is equal to 3.59 times 10 to the 7th meters. Well, that seems like a lot. How big is that? 35,900 kilometers. And that, when we convert back to miles, is around 22,300 miles. So think about that. To get a satellite in geosynchronous orbit, we have to put it almost 100 times as high as the International Space Station that was around 250 miles. That's crazy. It's ridiculous. It's almost 10% of the way to the moon, to be honest with you. But that's what we've got to do. There's only that one elevation where that's going to work. Well, now, how would I find the orbital speed of this? Well, I can go back to this now that I know my... That is fantastic. Also, now that I know my R. My R is not going to be radius to the Earth, and it's not going to be the altitude. It's actually going to be this R that I found before, which is the distance the satellite is orbiting from the center of the Earth. So I'm going to go over here. So that's 6.67 times 10 to the negative 11th, 5.98 times 10 to the 24th. Hope that's still on the screen. Barely is. And all that's over the 4.225 times 10 to the 7th meters. So V orbit, or obit, if that's kind of bad, that's an obituary. In this case, is going to actually be 3,070 meters per second. That's pretty slow compared to the International Space Station, which is going around, I think somewhere, takes an hour and a half. The Earth's circumference is around 22,000 miles. It's a little higher than that. So, I don't know, maybe 17,000 miles an hour. Oh, I should have that in meters per second. But anyhow, that's a lot slower than the thing which is closer. Anyhow, that's the last example. Thanks.